Let's say we have a biased coin and it has a probability 3/4 of coming up heads, which I'll call P. This coin could actually be a visitor to a web page who has a 3/4 probability of clicking a button, but I'm going to do this example with coins for simplicity. We'll define success to be heads and failure to be tails. This doesn't necessarily mean we're upset if we get a tails, it's just a way of specifying what the two outcomes are. Now let's say we flip the coin 10 times. How many times will it come up heads? Of course, it could come up heads 0 times, 10 times, or anything in between, but some outcomes will be more likely than others. If we mark the probability of each number of heads, we'll get something that looks like this. As you can see, the most likely results are 7 or 8 heads, but anything between 6 and 9 is reasonably likely. Like Carrie mentioned, this distribution is called a binomial distribution, and we can draw it for any number of flips. To make it easier to do this, I'll relabel this axis as the percentage of flips that came up heads, or the fraction. As you increase n, the binomial distribution starts to look more and more like a normal distribution. Here you see the binomial distribution with n equals 30, and the normal distribution overlaid in blue. The binomial and the normal distribution that approximate it will have the same mean, which will be equal to p, the probability that the coin comes up heads. And the standard deviation will be the square root of p times 1 minus p over n, where n is the total number of flips. Now in this case, we assumed that we knew the probability that the coin would come up heads. Let's instead consider a case where we don't know that. We flip the coin 20 times, so n equals 20, and it comes up heads 16 times, which I'll call x. Now let's say we want to estimate the probability the coin will come up heads. That is, we want to guess the bias of the coin. Of course, this could be a fair coin that happened to come up heads more than tails, but the results we saw will be more likely if the coin is biased. To estimate the bias, which I'll call p hat, it's an estimate of the probability, we'll take the number of heads, in this case 16, and divide by the number of flips, in this case 20, and we get 4/5. So our best estimate is that this coin has a probability 4/5 of coming up heads. If you'd like to see more details on what the binomial distribution looks like for different parameters, the page linked in the instructor's notes may be helpful. In order to use the binomial distribution, a few assumptions have to hold. First, there have to be exactly 2 types of outcomes. We've been calling these success and failure. And second, the events have to be independent. Learning the outcome of one coin flip doesn't tell you anything about whether the next coin came up heads. And finally, the events need to follow an identical distribution. That is, the probability of success needs to be the same for all of them. In practice, identifying cases where your events are independent can be kind of tricky, so let's go over some examples. First, suppose you shuffle a deck of 52 cards, and you draw and hold the first 20 cards. Each card is an event, and the outcome is whether the card is red or black. Next, suppose you roll a die 50 times. Each roll is an event, and you choose to label 6 as a success and any other result as a failure. Next, suppose a search engine, such as Google, is measuring how often people click on search results after making a search. Each event is one search made on the search engine, and the outcome is whether the person clicked any link in the results. Next, suppose an online education company, like Udacity, is measuring how many of the students who enroll in a course complete it within 2 months. Each event is one student, and the outcome is whether the student has completed the course 2 months later. Finally, suppose an online shopping company, such as Amazon, is measuring how often items that are added to a shopping cart are purchased within a week. Each event is a single item, and the outcome is whether the item has been purchased a week later. For each of these situations, check the box if you think it is valid to assume a binomial distribution, and specifically, think about whether the events will be independent. Some of them are a bit subjective, but take your best guess.